Lesson 17, Kirchhoff's Laws and Circuit Analysis. In 1845, German physicist Gustav Kirchhoff investigated circuits. He identified and described two important laws. The first law is called Kirchhoff's voltage law. Kirchhoff's voltage law states, for any complete path in a circuit, the sum of the potential difference rises equals the sum of the potential difference drops. So voltage rises at batteries and generators, and voltage drops at motors, light bulbs, and resistors. Kirchhoff's voltage laws can be summarized in two equations, one for series circuits, which I'm going to highlight in blue, which states that the total voltage is equal to the sum of the individual voltage drops. So Vt is equal to V1 plus V2 plus V3. For parallel circuits, which I'm going to highlight in pink, the voltage is constant. So if you know the voltage at any point, you know the voltage at all points. So here we have a series circuit. And beside it, we have a parallel circuit. And we're going to examine Kirchhoff's laws and do some calculations using the equations for Kirchhoff's voltage law. So let's assume in the first example, we have two resistors, one with a voltage of 4 volts and one with a voltage of 3 volts. And I want to find the total voltage. Well, we can look at the equation for series circuits, and we know that the total voltage is equal to the sum of the individual voltages. So that's 4 volts plus 3 volts. If you add these together, the total voltage of this series circuit is 7 volts. So, if you wanted to know the voltage of this battery, you can add up the drops in voltage, and that will be equal to the total. So here we have a battery of 7 volts. Let's do an example with a parallel circuit. In this question, I'm going to get you to find the total voltage, the voltage past the first resistor, given that the voltage past the second resistor is 3 volts. If we look at Kirchhoff's law for parallel circuits, it says that the total voltage is equal to the voltage past item number 1 is equal to the voltage past item number 2 and the voltage past item number 3. So if you know the voltage anywhere, you know the voltage everywhere. So since I know that the voltage at this resistor is 3 volts, then I know all of the voltages. So the total voltage is equal to V1 is equal to V2 is equal to 3 volts. And if you added more branches, the total voltage would not change. Your voltage at each one of those new branches would also be 3 volts. Now Kirchhoff came up with a set of laws, again this time for current. And his law states that at any junction point in a circuit, the total current entering the junction equals the total current exiting the junction. So there are two equations, one of them for series. I'm going to highlight this one in blue. Which states that if you know the current at any point in a series circuit, you know the current at all points in a series circuit. The second is for parallel circuits, and Kirchhoff's law states if you know the total current, it is equal to the sum of the individual currents. So I1 plus I2 plus I3 equals I total. Let's do a similar example. This time we're going to use a series circuit and a parallel circuit. We'll start with the series circuit first. So we'll use Kirchhoff's law for series circuits. And in this question, what I want you to find is if we know the total current, so I'm just making up this example, the total current is 0.50 amps, then what is the current past resistor number 1 and what is the current past resistor number 2? Remember that Kirchhoff's law for current in series states that if you know the current at any point, then you know the current at all points. So in this case, IT equals I1 equals I2 equals 0.50 amps. So the current past the battery is 0.50 amps. The current along this conductor is 0.50 amps. The current at point 2 and the current at point 1 is constant. No matter how many loads you place in the circuit, the current in a series circuit will remain constant. Now, Kirchhoff's law for parallel circuits is a little bit different. Let's try an example. In this example, I'm going to tell you that the total current at the battery is 15 amps. And I don't know what the current past this first load or resistor is, but I do know that the current past the second load is 7 amps. So Kirchhoff's law for current in parallel circuits tells us that the total current is equal to the sum of the individual currents in parallel. So I can write this statement for a parallel circuit. IT equals I1 plus I2. Now what you want to do is solve for I1. So we're going to take this guy and bring it over the equal sign, and when we do, we get I1 is equal to I total minus I2. That's 15 amps minus 7 amps. And we end up with I1 is 8 amps. So, another way to look at it. If you know this plus this must equal 15, what must this answer be? What plus 7 equals 15? And the answer is 8. 8 plus 7 equals 15. All right. Next we have a set of rules for resistance in series and in parallel. So in series, the total resistance is equal to the sum of the individual resistances. So RT is equal to R1 plus R2 plus R3. For parallel circuits, this one's a little trickier. And the equation to calculate the total resistance is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, or however many resistors you have in the circuit. To best practice this, we're going to try an example. What we're going to do is we're going to find the total resistance for two resistors of 10 ohms and 40 ohms. In part A, we're going to calculate them in series, and in part B, we're going to calculate them in parallel. So let's draw what this will look like. We're going to do part A first, a series circuit. And I'm going to draw two resistors in series. 1, 2. This one is 10 ohms, and this one is 40 ohms. And I want to find the total resistance. So looking up here at Kirchhoff's law for resistors in series, you know that the total resistance is equal to the sum of the individual resistances. So we can say that RT is equal to R1 plus R2. That's 10 ohms plus 40 ohms. If you punch this into your calculator, the total resistance in this circuit is is 50 ohms. We'll do a second example. This time we're going to connect these two resistors in parallel. So I'm going to redraw this. And instead of drawing these in series, I'm going to draw them in parallel. This is R1 and this is R2, and we want to find the total resistance. We know that R1 is 10 ohms and R2 is 40 ohms. So we have to use this equation here, which states that 1 over RT is equal to 1 over R1 plus 1 over R2. So we're going to start solving, and we'll sub in our values. 1 over RT is equal to 1 over 10 ohms plus 1 over 40 ohms. If you add these fractions, the two numbers in the bottom are different, so you cannot just add these algebraically. What we need is a common denominator between 10 and 40. That number that is common between 10 and 40 is 40. So 1 over RT is equal to, we'll put the common denominator down, and then what do we multiply 10 by to get 40? We multiply 10 by the number 4 to get 40. Then what do we multiply 40 by to get 40? It's the number 1. 40 times 1 is 40. Hopefully you can review how to add and subtract fractions, because you'll need to use these mathematical skills in this unit. Since we have a common denominator, we can add the numerator together. 4 plus 1 is 5 over 40 ohms. Now, the whole point of this was to calculate the total resistance, calculate RT. But what we found is 1 over RT. So we need to find RT, not the inverse of RT, or 1 over RT. So what we need to do is flip both sides here. So we have RT over 1 is equal to 40 ohms over 5. 40 divided by 5 is 8 ohms. So the total resistance is 8 ohms. Let's do an example that has mixed series and parallel. So the first thing we're going to notice is that these two resistors here, R1 and R5, are in series with each other. They're along the same straight line. Then we notice that R2, R3, and R4, these guys are in parallel with each other. So what I first want to do is I want to identify any circuit components that are in simple parallel. So these three are in parallel, and I'm going to call this group of resistors A. So this is resistor A. To find the total of resistor A, since these are in parallel, we can use Kirchhoff's law, which tells us that 1 over RA is equal to 1 over 75 ohms plus 1 over 50 ohms plus 1 over 30 ohms. To find the total of this, we need to find a common denominator between 75, 50, and 30. And we can find the common denominator between 75, 50, and 30, and that's 150 ohms. What do we multiply 75 by to get 150? That's 3, or 2 rather. Always use a calculator, folks. What do we multiply 50 by? That's 3. And what do we multiply 30 by to get 150? That's 5. So we can add the numerator now. We have 2 plus 3 plus 5 is 10 divided by 150. And again, what we wanted to find was RA. What we have here is the inverse of RA. So I want to flip both of these sides, and we're going to be left with RA is equal to 150 ohms over 10. So RA is 15 ohms. So now what I want to do is I want to redraw this diagram, but I just want to include, we'll have these 2-cell batteries. We have R1, which is 12 ohms. And R5 is 18 ohms. And then I want to, instead of drawing all 3 of these, I know that the total of all 3 of these is 15 ohms because we just calculated it here. So I'm going to replace these all with a single resistor that is 15 ohms. And I'm going to call it RA. So if I want to find the total resistance, now I've reduced this complex circuit into a simple series circuit that only has one path. So if you look, this is one path. So if I want to find the total, I can just add these together. RT is equal to 12 ohms plus 18 ohms plus 15 ohms. And if you punch this into your calculator, you'll end up with 30 plus 15 is 45 ohms. So the total current, I'm just going to, for a second, erase all of this so we can see it nice and clearly. The total current, or the total resistance for this entire mixed series and parallel current circuit is 45 ohms. And we did that by first calculating the total of these 3 and then adding this one plus all of this, which was 15 ohms. Okay? What I want you to do is try the homework practice questions below. And when you're done, attempt the corresponding LMS quiz on your LMS page. Good luck.